All right, hello, this is Dr. P, and in this lecture video we will take a look at the synthesis of alkynes as well as some reactions of alkynes. Now, if we're going to prepare alkynes, really the only way to do it is by elimination reactions. So we're going to prepare them via elimination. And this is similar to alkenes. And I know in the alkene lectures I skipped over elimination reactions and ways of preparing alkenes. We'll talk more about elimination in chapter 11, but the first section of chapter 8, so chapter 8.1, section 8.1 does go over elimination reactions to make alkenes. So let me just show you what it looks like for alkenes. So we'd have some kind of alkyl halide, and we'll treat this with a base, and we'll end up getting our alkene. Okay, so we're removing one hydrogen and we're removing the bromine. Now, for alkynes, we're going to need a dihalide. We need two halogens. So we could have, let's say, R, C, C, R prime, H, H, Br, Br. And if we treat this with base, we'll get a fast initial reaction to give us a bromoalkene here, and then we'll get a continued but slower reaction to eliminate the other bromine and the hydrogen there. So that will give us our alkyne. Now we could use a different type of dihalide, and we refer to these as a vicinal dihalide if the bromines are on adjacent carbons, they're in the vicinity of each other, and this other type of dihalide, is called a geminal dihalide. We have two halogens, two bromines in this case, on the same carbon. Geminal coming from Gemini, the twins of Greek mythology. Now, the conditions here have to be very harsh, so we need very strongly basic conditions. So we could use KOH, so potassium hydroxide, which is fused, we say, which really just means molten, and something like around 200 degrees Celsius. If you just wrote a delta for heat when you're writing out this reagent, that's fine. Or we could use sodium amide, you might remember that, so sorry, NaNH2, NaNH2, and heat. followed by water to quench the reaction. And really, that's how we're going to make our alkynes. If you already have an alkyne and it's a terminal alkyne, you can make a longer, or turn it into a longer alkyne by reacting it with an alkyl halide. But we'll talk more about that in another lecture. All right. So let's take a look at some reactions of alkynes. Oh, let me put that back in frame. There we go. So our reactions of alkynes are actually going to be pretty similar to our reactions of alkenes. Okay, that CC triple bond is rich in pi electrons, and so we'll get a lot of addition reactions just like we did with alkenes. So we could, for example, do hydrogenation. If we use excess H2 and XS, the letters XS are the chemist's abbreviation for excess. If we use excess H2 and palladium or platinum, etc., nickel, whatever, we will add 2 equivalents of hydrogen and get an alkane. All right. Now, can we just get an alkene? So we can't simply use one equivalent of H2. And why is that? Well, if we tried to use one equivalent of H2, so let me write it out here. We can't do this. RC triple bond C R prime 1 EQ H2. And again, an equivalent means my moles of H2 are the same as my mole. If I'm adding 1 mole of H2 to this, it's a 1-to-1 molar ratio. So I've got 1 mole of that for every mole of that. I will get some of that, and I will get some of that, and I will have some unreacted starting material. I get a mixture of products. So we'll say won't just get this. And that's because, as we add the H2, so let's say 1 molecule of H2 adds to a molecule of the alkyne, making an alkene. Now another molecule of H2 could bump into that alkene and make the alkane. And with excess H2, we actually add to all of our alkynes to make all alkenes and all those resulting alkenes to make alkanes. And so we end up with just our alkane when we have excess. But what if we wanted to stop at the alkene? Well, we can do a couple of different reactions. One is we can use a poisoned catalyst. So that's a catalyst that will catalyze the reaction, but it's slowed down in some way. So for example, here palladium is our catalyst. And our example here is Lindlar's catalyst. Which involves using, oh gosh, it's like barium sulfate and a organic, like a quinoline type compound, and nickel to basically, you know, sort of gum up the nickel. I think that was the original. I'll have to look up what it is, but just write Lindlar's and you'll be fine. So it would look like this: R, C, triple bond C, R prime. And we will do H2 and Lindlar's. And because it's the same type of catalyst, a surface catalyst, we will get a cis alkene. Because again, remember, hydrogenation of alkenes is a syn process. So even with our poison catalyst, it's still a syn-type addition. The two hydrogens add to the same side, and we end up with a cis alkene. Or we could use a different mechanism. And what this involves is what we would call a dissolving metal reduction. And we'll go ahead and use sodium, and we will dissolve it in ammonia. I know, these are some crazy reagents. Liquid ammonia, so you have to do this at low temperature or high pressure, or both. And sodium, and what happens is that the sodium in the liquid ammonia gives up an electron, and basically you have solvated electrons. So your electrons are floating around in your ammonia solution, and then we will proceed with our hydrogenation via a radical mechanism. And that mechanism is beyond the scope of the course. I'm not sure if the text actually goes over it or not, but you don't have to worry about it. So just remember that if you want to just go to an alkane, your regular hydrogenation works. If you want to stop at a cis alkene, use a poisoned catalyst. So you can write Lindlar's. Or poison catalyst, for that matter. I'd accept that. And if you want to go to the transalkene, you have to use different reactants here. Sodium in liquid ammonia. And that liquid ammonia serves as the hydrogen source as well. All right. So that's hydrogenation. What else could we have? Hydration. Let's do hydration. There's our hydration. There we go. So if we take our alkyne and react it with a mercury, I believe it's Hg2SO4 and water, and then reduce it with sodium borohydride. Now what does this look like? This looks like oxymercuration, demercuration. We will get RC double bond O CH3 like that. Okay, it is a hydration of sorts. We are adding, we're net adding H2O, so we've got one hydrogen here, now we've got three, no oxygens, now we have one. So we are adding H2O, but instead of adding H to one carbon and OH to the other carbon, this is what we end up getting. This is a Markovnikov product. The oxygens on the more substituted carbon. Now, in reality, what you're getting is the following. You're getting, when we look at the mechanism, you're actually getting this species here, which is called an enol. En for alkene, ol for the alcohol. This is in equilibrium with the ketone. And the equilibrium usually favors the ketone. So you'll actually, by doing the oxymercuration, demercuration, initially make this type of species, but then that will isomerize into the ketone. Okay, if we wanted to do the opposite, if we wanted to do anti-Markovnikov, we could do our BH3.THF, and I think there are some other reagents that are used, but again, I'd have to get back to you. I might have mentioned them in the other lecture videos, but these give us now the aldehyde. So this is our anti-Markovnikov. All right. So same general idea, only the product is a little bit different. Okay, let me just draw a line here. And then the other group of reactions I wanted to mention in this video is oxidation. And so we can have, three bonds there, Wayne. There we go. We can have our alkyne, and we can do the equivalent of a hydroxylation. So let's use KMNO4, and just in water, and in this case neutral, we will get a diketone species. This is analogous to adding the two OHs, except we're adding just oxygens with the double bonds. Now, if we used hot KMNO4, and basic KMNO4, we added some hydroxide, and then quench the reaction with water and acid, we will get RC double bond O, OH plus HO, C double bond O, R prime. We will get 2 carboxylic acid. So again, this is our oxidative cleavage. Now, what if you wanted to get the aldehyde? You might think, well, let's try doing ozonolysis. And again, I could do O3 for my ozonolysis. I don't even need to use DMS here. Don't need dimethyl sulfide. Water works fine. The only problem is because you're adding to a triple bond, you initially, add your one oxygen to each because you form the ozonolide intermediate, 5-membered ring, 3 oxygens, and then the 2 carbons. You'll get cleavage of the bond, but you'll get more oxygens being added in. And there's no hydrogens to add in because you just have ozone. Okay, with an alkene, the hydrogens are already there, and they stay there because ozone isn't quite strong enough to blast it apart and stick in some oxygens. But since you don't have any hydrogens on these guys, you end up with the carboxylic acids as well. Now, if you wanted to do oxidative cleavage and end up with aldehydes, you'd actually have to do your oxidative cleavage and then reduce your carboxylic acids back to aldehydes. Or I suppose you could go ahead and use Lindlar's or use your sodium and liquid ammonia to generate an alkene and then do ozonolysis. Interesting. So there are a variety of ways that we could try to make things using these reactions. And in the next two lectures, lectures 1 and 2, I'll talk about some more reactions and then how we could possibly use the reactions to try to make something, a process that we know as synthesis. All right. Well, until then, stay safe out there. Bye now.